Okay, welcome to today's lecture. We left here last time at option pricing, and I guess before I start, I have to check whether we are all on the same page when it comes to financial derivatives. You all know what a financial derivative is, what an option is, what a plain vanilla European call, European put is. If that is the case, okay, perfect. We'll go straight to option pricing. As you probably know, the most famous model for option pricing is the Black-Scholes-Merton model. The Black-Scholes model assumes the underlying price to follow a diffusion process, more precisely a geometric Brownian motion, yielding that stock prices are log normally and log returns are normally distributed, and under the assumption of such a geometric Brownian motion. In the Black-Scholes model, you do a delta hedging, and under the assumptions of the model you get the Black-Scholes differential equation, which is solvable for plain vanilla options, but exactly for, and especially for exotic options, the differential equation has no solution, and you need numerical methods to come up with an option price, and actually that is usually what is referred to as computational finance. Every time you have an exotic option for which you do not have a Black-Scholes formula, you need the computer, you need numerical methods, you need, for example, binomial, trinomial, lattice procedures, or Monte Carlo simulation to come up with an option price, and that's what I want to show you today. We start with the binomial model, also the most famous variant, the Cox-Ross-Rubinstein model, and then later on we'll look at Monte Carlo simulation, and this is all more or less from the Brandi-Mate textbook, and there you can look all this up. On the first couple of slides, there are just some basic repetitions on options. There is an inner value, there is a time value, just meaning that right now, of course, if you were to exercise the option right now, you have an inner value, meaning that the option at execution right now is worth something, or it is worth nothing because you would let it expire. And if you still have some time on the term of your option, you could still make a little more money, or the option could still go into the money, meaning that there is some possibility of a higher value. And this is the time value of the option. Okay. Now, if you want to price an option, obviously you need to make assumptions on the option, and more importantly, you need to make assumptions on the market. Usually the most important assumption is, of course, that the market is arbitrage free. If the market is not arbitrage free, well, prices are completely off and are not in equilibrium, and it doesn't make sense to come up with a pricing model that is not in equilibrium or that is not arbitrage free. And there are some different ways to do this. There's risk neutral pricing. You can look at supply and demand. Another possibility is to use a hedging portfolio. Sometimes you can also come up with a self-financing arbitrage portfolio. Sometimes you can also come up with an option price via a duplication strategy. If you think about the Black-Scholes model. In the Black-Scholes model, you might remember this from my bachelor class, that in the Black-Scholes model, it's a duplication strategy. You want to take it's not really a duplication strategy. Does anyone know how you come up with the Black-Scholes model? What the proof for the Black-Scholes model? What does it do? It uses a delta hedge portfolio. You're taking the underlying and you're taking the option, and you are hedging the underlying by using the option, by going short in the option, And because this portfolio is delta hedged, it has a risk of 0. And if it has 0 risk, it should yield the same return as the risk-free rate. And then, of course, this is the arbitrage portfolio. If the portfolio consisting of the underlying and the hedging instrument, aka the option, if this portfolio is risk-free for arbitrage reasons and for the market to be arbitrage-free, it must have the same price as the alternative risk-free investment, which is, of course, the return is a risk-free rate. And then you have the arbitrage portfolio, and then it needs to have the same price. Yeah? This is done here. You have the underlying option and a risk-free 0 bond, and then obviously you know the price of the 0 bond, that's quite clear. And if the portfolio, the delta hedged portfolio, yields the same risk, it should also have the same return and the same price, and then you simply have to compare those two, and then you can get the price of the portfolio. And this is how it is done in the in the Black-Scholes model. It's a delta hedged portfolio consisting of the underlying and a short investment in the option, and then it is also risk-free. Okay. You can also duplicate the payments, and this is what we'll do in the binomial model. This is actually quite simple. Assume a very simple model in which you can start here at S0, and the price can only go up and down, and it's at first it's a 1 period model. The stock price can go up and it can go down. Let's assume we start at 100 and it can go up 120 and it can go down to 80. The strike is 100, meaning that obviously the option has 2 possible payouts, 20 and 0. Now we can also make some assumptions on the probabilities that the price will go up and go down, but we know that actually these are the 2 potential payouts of the option. And what we will do then is we'll just argue that obviously we are investing X in the underlying, we are investing X in the underlying and Y in the risk-free rate. For example, let's say we have 10% risk-free rate, and then in the up state here we would get 20, and in the down case we would get this. Obviously the risk-free rate is paid out in any of those 2 states. And then we have a very simple duplication strategy. We simply buy the underlying or sell it short, and we invest in the risk-free investment, and we duplicate those 2 payouts of the option, 20 and 0. And if you do this, you will actually come up with an optimal X and an optimal Y. And what is done in that case? Obviously X star times 100 plus Y star should give you the price of the option. You only need the 2 probabilities here. Actually, you don't even need the probabilities. Okay, this is what we'll do now. Option pricing with a discrete binomial lattice process. Why binomial? We'll see this later on, that in the end, the probabilities that we are looking at are coming from a binomial distribution. It's not a big surprise because the model, as I said, consists of the stock price that is assumed can only go up and down each period with a certain probability. Now, because we only have 2 states, this is a 2-state, 1-period state space model. The interesting thing here is obviously that the binomial model results from the fact that we only have 2 potential outcomes. And you might remember this from the introduction to statistics. Every time you have a lottery in which you have 2 different types of balls, red and blue, red or black, or ones and zeros, and you are drawing numbers, or you're drawing balls from this lottery in which you only have 2 kinds, this is a binomial distribution. Yeah? If you put those balls back into the lottery. And this is the same setting here. You have two states, can go up, it can go down. And we've just seen here that it's quite simple to come up with the price of the option. You simply have to duplicate it with the risk-free investment and the underlying. Now, this is necessary, obviously. We need the risk-free investment with the interest rate R, and we have a starting point S or S0, and it can go up and it can go down. And to make this more clear, we are writing S times U and S times D. U for up and D for down. Has anyone ever seen the binomial model for option pricing? Yeah, okay, but you are sitting in my risk management class. No, I will tell you that later. You will see that later. There is one interesting thing you will notice later on, that it's not that different from the Black-Scholes model. We'll start very basic, simple pricing result. If you have two payouts, C1 and C2, then the arbitrage-free price of any financial contract with these two payouts is given by 1 over 1 plus R times C1 Q plus C2 times 1 minus Q. And in this case, if we have two states, up and down, actually those two, they look like probabilities. Q and 1 minus Q are given by this. If you are interested in how to come up with this Q, take a look at my textbook, Unternehmerische Finanzpolitik. There should be a small section where it's quite simple to see if you only have two states, this Q here, this probability that is included in the arbitrage-free price can be derived quite simply. But this result is even more general. What does it state, this first line? It states that the arbitrage-free of any financial contract with two payouts is given by what? A Q and 1 minus Q, those resemble a probability of some sort. So if those are the two potential outcomes, C1 and C2, the term in brackets is an expected value. This is what? A discount factor with the risk-free rate, and we are using this probability Q, so let's just say it's an expected value under Q, with Q being these two probabilities. This is what in financial mathematics is referred to as risk-neutral pricing. The idea is the following. If we want to come up with a price for any financial instrument, what would we do? We would take all future outcomes, all future payouts, we would calculate the expected value, and then we would take the expected value and discount this expected value to calculate the present value of all future payments, but we would need an interest rate that includes the risk-free rate and a risk premium that is investor specific, because this investment has a certain amount of risk, but each investor has an individual risk preference. Some investors are risk neutral, some are risk friendly, some are risk averse. And if you are an investor that is risk friendly, you will have a different investor specific risk premium, and you will demand a different risk premium, and you will look at this price differently than another investor with a different risk preference. Meaning, if we want to price all financial instruments, we would have to look at all those investor-specific risk premium and all those different investor-specific discount factors. That's not really practical and it's not feasible. So what do? You simply assume that in an arbitrage-free model market, there should be some probabilities so that all prices are actually given by the expected values discounted with the risk-free rate. You simply assume that those prices were generated with all investors being risk neutral. If you're risk neutral, you're demanding the risk-free rate. And then, under this assumption, all prices should be generated under these probabilities, Q and 1 minus Q. And because this is done with a risk-free rate, this is called risk-neutral pricing. And these are called risk-neutral probabilities, in contrast to physical probabilities. Physical probabilities are the probabilities that you can observe in nature. And if you transform those physical probabilities into theoretical risk-neutral probabilities, so these are the probabilities under which all investors are assumed to be risk-neutral, and you can calculate prices simply by taking the discounted expected value with the risk-free rate, then those probabilities, if they exist, they are called risk-neutral probabilities or pseudo-probabilities. Now one has to be careful. Again, those risk-neutral probabilities, they are theoretical ones. You cannot observe them in the market. You can only observe physical probabilities, and then together with the prices, you can try to calculate those risk-neutral probabilities. And if you can find them, this is what we call the first fundamental theorem of asset pricing, der erste Hauptsatz der Bewertungstheorie. If there is at least one set of probabilities, or more precisely we speak of a probability measure, Wahrscheinlichkeitsmaß, if there is at least one risk-neutral probability measure, then the market is arbitrage-free. If this probability measure is unique, if those probabilities are unique, then the market is complete. Yeah? I'll repeat it in German to stress this. Das ist in der Finanzmathematik das zentrale Ergebnis. Wenn Sie einen Markt auf Arbitragefreiheit überprüfen möchten, müssen Sie zeigen, dass es solche Wahrscheinlichkeiten gibt. Das ist der einfachste Fall, dass es eigentlich nur bei zwei Zuständen, dass es eine Wahrscheinlichkeit und Gegenwahrscheinlichkeit gibt. Wenn es so eine Wahrscheinlichkeit gibt, sodass sich alle Preise als diskontierter Erwartungswert aller zukünftigen Zahlungen darstellen lässt, dann ist der Markt arbitragefrei. Und wenn dann diese Wahrscheinlichkeit noch eindeutig ist, dann ist der Markt vollständig, bedeutend, dass Sie jede Zahlungsreihe darstellen können mit den am Markt gehandelten Wertpapieren. Again, you can see some basics of financial mathematics, or mathematical finance more precisely. In mathematical finance, I told you that you're usually not using risk-free rates, but you're using zero bonds. Here you can also see why, because you can just look at zero bonds, and you take a zero bond and you multiply the zero bonds with the expected value of those future cash flows, and then you should get the prices. Next, you need the existence of such a risk-neutral probability measure to show that the market is arbitrage-free. And the idea is simply that instead of looking at investor-specific risk premia and interest rates and discount factors, you want to simplify it, and you simply incorporate all those informations in the probabilities. And because you are changing the physical probabilities to something that is theoretical, these are called risk-neutral probabilities or pseudo-probabilities. And in this simple scenario with only two states, with an up or down state, this here is the result. You can look it up in the textbooks, because this is a very simple market with one instrument and two states. You can quite easily show, yes, in this scenario there is one probability, and the probability can be calculated by 1 plus r minus d over u minus d. And this is the first result here, and if you choose q like this, then the prices are arbitrage free. Yeah? Okay. Now, if we know that this here should be the arbitrage-free price, we can simply duplicate the financial contract in T1. And this is a very simple example. Risk-free rate 10%, current price is 100, can go up to 125 and can go down to 80. You can see that actually here U and D, those are not really probabilities, but you can see that actually as U and D are the relative changes. For example, U is 125% and D is 80%. Okay. Now we're looking at a put option with the underlying price as the strike, and here you can see the potential outcomes, 125, 80. So in this case we are getting 0, in this case we'll get 20, and we want to duplicate those two payments. This is the thing I've shown you before, just with some numbers. 125 times x plus 1.1 times y should equal 0, and then 80x plus 1.1 times y should be equal to 20. The solution is that we'll go short in the underlying and we'll invest in the risk-free investment. The portfolio should have the same price as the put option, and you simply get P0, the price of the option should be 6.06. So without even looking at the probabilities and the risk-neutral pricing, you can come up with the option price quite simply, because it's a very simple model. One period, two states. Again, these are the risk-neutral probabilities or pseudo-probabilities. This is also called martingale pricing, because it's a martingale mass. I will not go into the specifics of martingales. It suffices to say that in mathematical finance, you're looking at probabilities, probability measures, and you make certain assumptions on those probabilities, and you want those probabilities to resemble some type of a fair game. You know? And a martingale measure is something that models a fair game, more or less. Okay, so one could have also calculated the price with the risk-neutral probabilities. Next, the idea is how can we generalize this to multi-periods? Quite simple. You simply assume that in T1, this is again an option, and you can generalize it by simply adding yet another two sets of two states. So we now assume this little example that we have a call option with maturity in 2 periods and a strike of 90. So it can go up and it can go down again. And we calculate the price of the option simply by looking at this payment and this payment. Then we get this point, and we do the same here, and then we get the payout here, and then we do it yet another time to get C0, the price of the call option. Yes, you simply repeat this process recursively, going from right to left. And this is shown here. You have 125 and 80 times 125%. Then it can go down up here, or it can go down again. And you now get 3 states. And then you go up and down. You can duplicate those payments, CU and CD in t equal to 1, again by using the underlying and the risk-free investment, and this is how you get those two payments here, CU and CD, and then you take CU and CD and come up with the option price. So it's quite simple to generalize it to a multi-period model. You simply repeat this over and over and over again with yet another duplication portfolio. Okay. And in the end, here, for example, you'll get a price of 28. Okay. Now, let's take a closer look at this risk-neutral pricing approach. We know that for a call option, we have the final terminal payouts at maturity, and in risk-neutral pricing, we take the expected value of all future payments, discounted with the risk-free rate under the risk-neutral probability measure. So we need those probabilities Q. We are discounting with the use of the risk-free rate, and we know the future potential payouts of the option. Now for the binomial process, for this two-state model, you can show that Q and 1 minus Q are given by these terms here. And what do we do next? What is the probability of having a stock price at maturity that has started at S and that has gone up J times and gone down T minus J times? So we start at S and we can go up and go up 2 times. So in this case, J would be equal to 2 and T minus J would be 0. We can go up once and go down once. So J would be 1 and T minus J would be 1, and so on. So J, the index J, is the number of times we've gone up. And if we've gone up 5 times, we can have gone down only T minus 5 times. This probability here is what? Is simply T over J times Q taken to the Jth power times 1 minus Q taken to the T minus Jth power. This is quite simple. Again, remember, it's a lottery with 2 outcomes, and you are grabbing into this lottery without putting the balls back. We can only go up J time, and if we've gone up J times, we can only go down T minus J times. It's the same with the lottery with black and red balls. If you take out 5 red balls, there are not any red balls left. You can only pull out black balls, for example, and the probabilities change. And those probabilities here, they are Q and 1 minus Q. So it's a very simple binomial probability. Now, the payout, CT, for a call option is given by the maximum of the final stock price minus the strike and 0. So risk-neutral pricing is what? Discount factor times the expected value under Q of CT. Okay, so let's do this. The discount factor is this here. Risk-free rate, that's done. Expected value for a discrete random variable is the sum of the outcomes weighted with the probabilities. Yeah? Remember, expected value of x is simply the sum of all x times the probabilities, right, in the discrete case. And this here, this is the probability, and this here, this is the x. So you're summing up those probabilities here, we've seen that here, and these are the payouts. And we are not writing CT, but remember, we start at x and go up j times, and we go down t minus j times. So this here is ST. Okay, so in the end, let me just delete a little bit. So in the end, we'll get the option price with risk-neutral pricing as the discounted at the risk-free rate expected value of all future payouts of the option. If we are looking at the price of the option, not today, but at a future point t before maturity, it's slightly different. You can see that there is just this difference here, and we are not going just until maturity capital T, but we're going until capital T minus T. And again here it's the same, and so on and so on. But otherwise it's the same. Okay. Let's now define A as A dash for a natural number, or A dash plus 1 otherwise, and A dash being the logarithm of x over st times d taken to the tth minus tth power over the logarithm of u over d. Do not think too much about why we are using, I think this is in German it's a Gaußsche Klammer. This way of taking the integer. And don't think about how we defined A dash. You don't have to care. It's simply a trick to do the following. Look at this. Now if we look at CT here, the price of the option at a given point t, we still have this maximum function here. And now look at this. It's the same, CT here and CT here, they stay the same. The only difference is that this here is now gone and this here is A. This is the only difference between those two formulas, and we want to eliminate this maximum function because this causes some problems. And we now have a very nice sum here. The maximum function has gone, and we need this strange definition of A here for this. This is the only reason. And now you can see that the option price is what? It's simply a sum of some weighted payouts of the underlying, and you can easily calculate all these terms. And if we now take this here, you can see that actually this is I think the survival function, not the distribution function, but the survival function of the binomially distributed random variable. So in German it's 1 minus die Verteilungsfunktion einer Binomialverteilung. If you take this here, and if you substitute q times u over 1 plus r, and you simply write it with q tilde, you can see that in the binomial model, the price of a call option is given by stock price times binomially distributed probability minus strike times discount factor times probability. And you might remember this from the Black-Scholes model. In the Black-Scholes model, it looks like this. St times n d1 minus x e minus r t minus t times n d2. And it is no coincidence that this pricing formula looks very much like the Black-Scholes model. Actually, do you know what has happened? Yeah?
Maybe there are an infinite number of intervals.
Yeah.
So
if you simply...
binomial model converge to the normal distribution.
Yeah. This is a very famous result. One would think that the Black-Scholes model is the general case. Well, it's not. The general case, the more general case, is the binomial model. If you take the binomial model and increase the number of steps, you will get the Black-Scholes model as the limiting case. So if you simply take the number of steps, the number of periods, and let it go to infinity, the Black-Scholes model is the limiting case of the binomial model, which makes sense because you are taking, for example, 1 year, and you can cut it up in 12 months in 4 quarters, or you can simply cut this 1 year into an infinitely high number of small little timestamps. And if you do this, you will get the Black-Scholes model. Again in German. Das Black-Scholes-Modell ist einfach der Grenzfall des Binomialmodells. Wenn Sie einfach die Zeit immer kleiner werden lassen, haben Sie das Black-Scholes-Modell in stetiger Zeit als Grenzfall, als Spezialfall des Binomialmodells. Das Binomialmodell ist ein Pricing-Modell, ist ein Bewertungsmodell in diskreter Zeit und es ist letztlich das Black-Scholes-Modell, wenn Sie einfach nur die Zeitabstände immer kleiner werden lassen. Und deswegen überrascht es jetzt auch nicht, dass letztlich die Struktur exakt die gleiche ist, nur anstatt der Binomialverteilung haben Sie oben die Normalverteilung und anstatt des diskreten Diskontierungsfaktors haben Sie hier einen stetigen Diskontierungsfaktor. Das ist alles. Alles andere ist gleich. Ne? Also letztlich die Modelle sind quasi identisch oder äquivalent. Okay. This is just what I just said. The binomial lattice process is the limiting case. Oh no, if you let the time steps become smaller and smaller, you will get the geometric Brownian motion. You substitute the discount factor, and again, for n to infinity, the Black-Scholes pricing model is the limiting case of the binomial model. So remember this. This is here, obviously, the Black-Scholes pricing formula. Okay. Just one side note. You might know this. Perhaps it's new. You've seen that in the Black-Scholes model, the volatility of the underlying is an input parameter. And in practice, you can differentiate between the historical volatility and the volatility that is implied by the Black-Scholes model. How does it work? Now let's assume you have a historical volatility, sigma h. You put it into the Black-Scholes model and you get a price from Black-Scholes. This is the historical volatility. Now if you go just to the market and you see an actual price and you try to set it equal to the Black-Scholes model, you can just look at this as a function in the volatility, and you select the volatility such that the Black-Scholes price is equal to the actual market price you can observe in reality. And if you use this volatility here, this is called the implied volatility. Why implied? Because this is the volatility that is implied by the Black-Scholes model if it is set equal to the market price. Implied volatility and historical volatility obviously do not have to be equal. They do not need to match. What one can see is usually that the implied volatility varies with different strikes, and it looks like this. And this is the famous volatility smile. It looks like a smiling face, and this is the volatility smile. And this is the fact that empirically the implied volatility varies with different strikes. Okay. Another set of important model parameters and input parameters are the option sensitivities, the price sensitivities. Those are the partial derivatives of the option price with respect to the different input factors. Now, the first one is the delta. The partial derivative with respect to the maturity is the option theta. We have an option gamma, we have an option rho, and although this is not a Greek letter, it's called the option vega, the price sensitivity with respect to volatility. If you talk to a quant or an investment banker, first thing he'll say is that everyone uses Black-Scholes. And it's quite interesting that they will usually not work with prices. No one cares about the option prices. What they care about are the option Greeks, because options are usually used for hedging, and for hedging they immediately use the Greeks, the sensitivities. And we've seen this in the Black-Scholes, the derivation of the Black-Scholes model. It's quite simple, because if you take a number delta of options of, I think, put options, and you want to hedge a number of one underlying, it's a famous result from the Black-Scholes model that you have to set your the number of options you need to fully hedge this portfolio of underlyings. You need to set it equal to the option delta. And that is why it's called a delta hedge, or a delta hedge portfolio. Actually, this is not surprising. The sensitivity of the option with respect to the underlying price, and if you want to hedge the underlying, then it makes sense to use the delta as the number of options to fully hedge this portfolio. And this is why these Greeks are obviously quite important. Now, we've seen this in the discrete case. Now let's generalize the risk-neutral pricing formula. We are now using a continuous discount factor, and we are using these probabilities P and 1 minus P. Again, those are risk-neutral, pseudo-risk-neutral probabilities, now here with the continuous interest rate. Again, U and D, those are the probabilities for the underlying to go up and to go down. And one can now try to use a binomial model, a trinomial model, or later on even a Monte Carlo simulation and finite differences to discretize this model. Now, if we were able to find a solution to the Black-Scholes differential equation, and if we had a Black-Scholes pricing formula for any type of option, we would not need any of these methods. But because continuous or pricing in continuous time is usually so complicated that for more complicated options we do not have a Black-Scholes pricing formula, we need to resort to these types of alternative methods to come up with a pricing formula. And the basic idea usually is if we cannot do it in continuous time, let's use discrete time. If we cannot do it in continuous time for 1 year, simply divide it up into 12 months and try a discretization strategy. So let's try it first with the binomial model. We are assuming U is equal to 1 over D. This is an assumption we make. So S times U times D again is S. And this is SU squared. S times U taken to the third power, and so on. And what happens now? Now, in any of these cases, we are trying to approximate the continuous stochastic process. For example, S, the geometric Brownian motion, ds, the change in the underlying price is given by Rs dt plus sigma S dw. And we want this approximation to be as good as possible. Now, how do we do this? We simply look for some parameters, for some values of the initial process, and we set it equal to the parameters we get for our approximation. For example, we want to look at this stock price ST, or the next stock price ST plus delta T. Now, in continuous time, with a geometric Brownian motion, we know that the log returns are normally distributed. So the logarithmic change in the stock price is normally distributed with these two parameters. Okay. Now, ideally, we would see that here the expected value of the relative return, or the discrete return, is the exponential function of Rd delta T. The variance can also be calculated with this. Now, these two should be equal for the discrete approximation as well. Again, we in the population we have a continuous stochastic process, and we need an approximation. And what we do is we at least require the approximation to have the same mean and the same variance as the initial process. So this is what we want. For the binomial process, if we discretize this, you can simply calculate that the change, or the expected future stock price is given by P times U times ST plus 1 minus P times D times ST. Not a big surprise. What is the expected future stock price? Well, the stock price can only go up, it can go down. So we start at ST times P times U and the other alternative. So this is the mean. Das ist der Erwartungswert der zukünftigen Zahlung auf dem Binomialgitterprozess. Das hier sind Erwartungswert und Varianz für den eigentlichen stochastischen Prozess, die geometrische Brownsche Bewegung, die wir approximieren wollen. Ja? Und die Idee ist jetzt natürlich, dass wir die Approximation nicht perfekt hinbekommen werden. Also werden wir aber zumindest fordern, dass beide den gleichen Erwartungswert und die gleiche Varianz besitzen. So let's do this. We have the two expected values. We set them equal and we require that the expected future payout on the geometric Brownian motion is the same as with the approximation, the binomial lattice. If we get this, you can see that P should be equal to, well, actually you can now see how we can come up with these pseudo risk neutral probabilities. This is the result here. You can get the pseudo risk neutral probabilities by simply assuming that the model it can go up, and if it goes down, it goes back to its initial level. And then, under this assumption, you get the pseudo risk neutral probabilities. We do the same for the variances. You don't need to memorize all these formulas. What you need to remember is that you're trying to approximate the geometric Brownian motion with a very simple discrete lattice, discretes Gitter, and you require expected value and variance to be equal for both the geometric Brownian motion and the binomial lattice process. If you set it equal, you will get this here. Looks awful. You can simplify it even a little bit. We are assuming U is equal to 1 over D, and then we calculate a lot, and in the end you can see that U is almost equal to the exponential function of sigma times the square root of delta t. This is the Cox-Ross-Rubinstein model, or Rubinstein model. If we take the binomial model, a binomial lattice, and we set U equal to this expression, D equal to this expression, so U is equal to 1 over D, and we use the pseudo risk neutral probabilities. This is the Cox-Ross-Rubinstein model, also abbreviated CRR. This is the most famous case, I would guess, and the most famous example of a binomial lattice process for option pricing. You could also argue, okay, let's just use 50%, 1/2 probability. Then you're not setting this, but you're setting this. And if you set this, you will get slightly different U's and D's. Obviously, it could look like this now. It does not necessarily mean that if you go up and go down again, you will get to the initial ST or S0. But it might be that the lattice will look slightly different. In the first case of the Cox-Ross-Rubinstein model, this is the special case where if you go up and go down, you will get to the same point from which you have started. Why? Because U is set to 1 over D. The Jarrow-Rudd model is slightly different. It's a different calibration of a binomial lattice process. Here you can also see why it's not formally correct to speak of the binomial model. Actually, there are a couple of models that use a binomial discretization strategy to approximate an option price. Okay, so this is the Gero-Rudd model. There are some alternatives, and let's now look at how it is done in MATLAB. We are looking at a very simple European plain vanilla call. S0 is equal to K, the strike, 10% risk-free rate, volatility 30%, and half a year. At this point, you would immediately say, why do we need a discretization thread? We are not needing it. For this very plain vanilla European call, use Black-Scholes. Why should you use a binomial lattice if you can use Black-Scholes? It's just for illustration. And later on, we will assume that the true price is given by the Black-Scholes price. That is an assumption. We are not talking about market prices. Market prices can be equal to the Black-Scholes price. They can be off both prices. But for illustration, we assume that the Black-Scholes price is the true price. That's the actual price. In this case, it's 6.1165. We discretize this half a year in steps of 1 month. So we have delta t is equal to 1/12. U, D, and those pseudo risk neutral probabilities, they are given by these quantities. And here you can see that it's not equal to 50%. It's slightly different to 50%.
Excuse me.
Yeah?
Why is, if we want to discretize in monthly periods and we have half a year, why do we take delta t 1/12 and not 1/6?
Because later on we'll use 6 steps. We'll use 6 steps. But let's remember this when we get to the MATLAB program. I hope that this is true. Let me just check that. This is the S0 K R T sigma T sigma N. T sigma N. Actually, I don't really know right now why I put this in here. Why did I use 5 months? Might simply be an error in the program. Shouldn't make such a big difference here, but I think at this point, at least here, it would make sense to put it 6/12 and 6 steps. Yeah. Because as you can see later on, we're using 500 steps and 1,000 steps, and we're increasing the number of steps by which we are dividing this. And in the program itself, you are immediately calculating t over n. So you're taking t, which in this case would be 5 months divided by 5 steps, or 5 months divided by 500 steps. And it would be interesting, you could do this at home. It might be that actually I've also calculated the Black-Scholes price with 5 months instead of 6 months. But you can check that at home. Now, this is how it would look like in the binomial lattice. This is the stock price. It can go up, it can go down, and so on and so on. And you have these prices. Then obviously you can calculate for the last column, you can immediately calculate the payouts. Then you will get those payouts. Those are for a call, this is CT. And then you can go back recursively, take those two and calculate this one. Then you take those two and calculate this one. You take those two and calculate this one, and so on. And then you go back one period and back and back and back, and you get 6.36. Now, in the last column, you can see the payoff profile, and then you go back from right to left recursively. And one example is given by this. You need to weight, you need the probabilities, the risk-neutral probabilities as weights, and then obviously you are taking the risk-free rate and do continuous discounting, and then you get those 29.77, which is this value here. You take the 39.07 and 2070, and you take the probability P and 1 minus P, you have to discount it, and then you get the price in the next left column here, 29.77 here. And then you take those two, go back, those two, go back, those two, go back, and those two, and you have this 636. As you can see, with just 1, 2, 3, 4, 5 steps, it will yield a price of 636, which is already close to the true Black-Scholes price, but it's not equal to the Black-Scholes price. And to implement this in MATLAB, it's a little bit tricky because we want to save variables, we want to save memory, we want to save time. What do? We take Fij as the option price in node ij. Variable j denotes the time at which we are looking, j times delta t, and the variable I is the node, is for the ith node at point j. And we are counting from below upwards. N is the number of intervals we're looking at. So delta t is t over n. Then the underlying price in this node ij is given by initial price, you go up j times, I times, and you go down j minus I times. This here is, I think, a slight typo. I think you have to correct this here. Fin, obviously at maturity, you know the terminal values of the option. Those are just the payoff profiles. And for any period, any previous period j, Fij is probability times one payout plus 1 minus p times the other payout and discounted. And this is the function how it looks in MATLAB. You want as an output the price and the lattice. You have as input parameters the current stock price, strike, risk-free rate, t, sigma, and the number of intervals. And you immediately calculate delta n, u, d, and p. And you initialize the lattice as zeros, as a matrix with the zeros. And then in the last column, you can immediately write down all those option payouts. And this here is just, no, this here. This is this step. This is this. For the last column, we can immediately insert into the matrix the values of the option payouts. And then we need two for loops. We go back from right to left, one column, and then we have to go from bottom to top or bottom to top or top to bottom. You can decide on what you want to do. You go back one column, so from n minus 1 to 0 in steps of minus 1. So you start with n minus 1, n minus 2, n minus 3 until 0. And then you go from bottom to top and you calculate all those prices you have here. So this is n minus 1. n minus 2, and you start here, take this and this, or more or less, no, you start here, and you calculate this, then you take this, and you calculate this, and you go up. If you are done, jump to n minus 2. And so on. This is how this double for loop works. And in the end, price is what? It's the entry 1, 1. Just this one here. This very simple program. So let's do it in this example with 500, and 1000 steps, and you can see you are getting closer to the Black-Scholes price, which is the result that obviously the Black-Scholes price is a limiting case for n to infinity. Now to show this graphically, I've used this small program, quite simple. It simply starts with one interval, and it moves up the number of intervals and then plots all the different prices from the binomial model. This here, this is the Black-Scholes price. And you can see that the price from the binomial model zigzags around the Black-Scholes price, and it slowly converges. Yeah? But as you can see, there is not much improvement, say after 20 intervals, and it zigzags around here. Now for an optimization algorithm, zigzagging and such a convergence behavior is very bad. And you can see that, and for us it's actually quite nice, because you can see that even with just 5 intervals, the result is already pretty good. It doesn't get much better afterwards. But for an optimization, if this were an optimization algorithm, this would be a very bad behavior, very bad convergence. Okay, so this is a convergence of the binomial model. You can even improve on this program by considering in the Cox-Ross-Rubinstein model the fact that if you take a look at those prices here, not here, but here, 1, 2, 3, 3, 4, 4. Most of these underlying prices, now 5, 5, 6, 6, 6, most of these underlying prices are identical. And you don't need a matrix. So remember, the way the program is programmed right now, it looks like this. It is a matrix. And we are using up a lot of computer memory. And just on a side note, this is not a very efficient way of programming this. You can just, if you see this is a Cox-Ross-Rubinstein variant, you can simply say, okay, I'm not using a matrix like it is done here. Look at this, n plus 1, n plus 1. This is a matrix here. You can just use a variant. You can, first of all, you can pre-compute invariant quantities. Also, if you write such a program, always remember that it doesn't make too much sense to include calculations that are done over and over again in a loop, because then the computer will repeat the same and the very same calculations over and over again and use up time and memory. So you can actually pre-compute a couple of invariant quantities that stay the same for all calculations. Delta t, u, d, p, but also the discount factor, and p times u and p times d, which is just the discount factor times p and the discount factor times p 1 minus p. Then you set up the s values, and you don't need a matrix, you just need a vector. So you can save on some memory here. And then it's quite simple, and it looks slightly different, but it's the same result. It's just faster and uses less memory. Now, the price again is then the last value of this vector and not C or lattice 1, 1, the 1 point in the matrix, but it's a vector. Okay. Trinomial. A trinomial model is what? We've seen a binomial model. What is a trinomial model? A three-state model. The stock price can now go up, it can go down, and it can stay the same. That's the only difference between the binomial and the trinomial model. As you can see, it gets more complicated. We again want to approximate the geometric Brownian motion from the continuous case. We will now set, for example, the expected value of this logarithmic change in the stock price squared, and because we now have three probabilities, we require that PU plus PM plus PD is equal to 1, so that they add up to 1 such a way that they are probabilities. Those are the requirements we need the lattice to fulfill. And then we get PU, PD, and PM. This looks horrible, and it is horrible. You don't need to remember this. And in the end, if you take this, it's simply a question of coding this in MATLAB and proving that this is true. And we don't actually need this. If we take a European plain vanilla call, you can calculate those three probabilities here, and we'll just do it in MATLAB. Again, with the current stock price, strike, risk-free rate T, sigma, and delta LNS. We pre-compute all those invariant quantities, delta N, nu, the discount factor, PU, PM, and PD. You see that I already include the discount factor times the probability to go up, stay the same, or go down. Then I'll set up the S values at maturity. Those are the stock prices in the last column. Then I'll set up the lattice. You can see this is again the initialization of the payout profiles in the last column of the option. And then this is going back one column, one column, one column, and finally I get the price here in the last step. Here this is the same, just programmed in a slightly different way. And we can do this here again. N is equal to 3 steps, 1,000, 1,000 steps, and you can see that we get the true Black-Scholes price with 14.7171, and even with just 3 steps, it's already a very good approximation. Why? There are 2 sources that can, or 2 ways of improving on this discrete model to get it closer to the Black-Scholes model. The first thing is just to use more intervals. That will move the model into the direction of the Black-Scholes model, or you can make it more flexible by allowing the stock price to go up, go down, or stay the same. Obviously, this is more flexible than the binomial model. And then we need a couple of steps and a couple of intervals less, and we'll already get a very close approximation to the Black-Scholes price. Okay. This is how it looks like graphically. Can go up, can go down, can stay the same. And here again, you have this, these option payouts, and then you go back, and you get this price of 1464.94. This is the trinomial lattice process. Okay. Now, those are 2 very simple, more or less simple ways of discretizing time and using a discrete time approach to approximate the continuous time model given by Black-Scholes. Next, we do Monte Carlo simulation. Monte Carlo simulation is actually even more simple than binomial and trinomial. Remember that Black-Scholes model hinges on the assumption that ds, t, is some kind of continuous stochastic process. For example, mu st dt plus sigma st dwt with a Wiener process. We have a Wiener process, a very simple model for a stochastic process with independent, normally distributed increments, and you include a drift, you include a diffusion, you have a geometric Brownian motion, and in the end, in the Black-Scholes model, we get a differential equation, and if the option is very simple, if it's a plain vanilla option, we can solve the equation. If not, we cannot. And usually the question whether we can solve for the Black-Scholes differential equation hinges on the question and is dependent on the question whether the payout here just depends on the stock price at this point, ST, or whether, for example, it is the maximum or the minimum, or whether it's the average of all stock prices in between. Now, what can you do? Monte Carlo simulation. What is Monte Carlo simulation? If I'm mean, I would ask the fellow student who attended yesterday's lecture. Does anyone know what Monte Carlo simulation means? Yeah.
So you multiply or add up different distributions that can be really calculated or difficult to calculate otherwise. So
yeah.
it's more like so you're making
You're having the right idea. This sounds pretty much like the approach we take in risk management when calculating the valued risk. Monte Carlo simulation is actually even more general. Monte Carlo simulation simply means that you have a theoretical distribution and you generate random numbers from this theoretical distribution. Now, usually in statistics, the approach is you have a population, you draw a sample. For example, I would ask you for your age, and then I take this sample and I try to make inferential statements on the distribution in the whole population. For example, I would calculate the mean and the standard deviation of your ages, and I would say, well, the population of all students has an average age of la la la. And age is distributed according to a normal distribution, Pareto distribution, or whatever. This is usually what we do in inferential statistics. You could also do it the other way around. You simply take a theoretical distribution for which you have a distribution function, or a quantile function, or a density function, and you try to find an algorithm with which you can simulate numbers that are distributed perfectly, 100% according to this distribution. And the most basic example is throwing a dice. If I have a fair dice, I simply know that the numbers 1, 2, 3, 4, 5, 6 are distributed according to a what type of distribution? A uniform distribution. In German, Gleichverteilung, a uniform distribution on the set of numbers 1, 2, 3, 4, 5, 6. This is the discrete case. You can also have it on a continuous interval. And you all have this on your calculator. If you have a calculator and it has a random number generator, this is basically the same. It generates random numbers from a uniform distribution on the interval of 0 to 1. We'll get you some numbers. Now with the dice, it's quite clear. I throw the dice 3 times. I get 3, 1, 3. Doesn't say too much about the distribution. But the basic idea in Monte Carlo simulation is that if you just generate a high enough and large enough number of random numbers, those observations will stabilize with their empirical probabilities according to the probabilities in the distribution. So if I throw the dice 1 million times, or let's say 6 million times, I would expect about 1 million ones, 1 million twos, and so on. So just by generating random numbers from a distribution, you can get numbers that stabilize with their probabilities according to this distribution from which you are calculating and simulating. Now let's do this in R. I did this yesterday, so let's do it here as well. From which distribution do you want to generate some numbers? Student, T, normal. Yesterday I used the normal. Let's use now the student's T number, student's T distribution. As you know, the student T distribution has one parameter, the degrees of freedom, that's df. Oh no, this is 100. And you get 100 random numbers from a student's T distribution with 3 degrees of freedom. Let's plot this. I'm now using a histogram. Oh. This is what we get for 100 numbers. As you probably know, this does not yet look like a student T distribution because I think, if I'm not very much mistaken, it's symmetrical around 0. So let's take 1000 and now let's take 100,000. Doesn't really look too nice, so let's not use a histogram but a density estimator. Here you have 100,000 random numbers from a student's T distribution with 3 degrees of freedom. Let's take another distribution. 77 now looks like this. You can do the same for a normal distribution, R norm, and just need different parameters. Now let's say 24 and 4. And now you get a normal distribution. This is Monte Carlo simulation. Why it's called Monte Carlo simulation? Because people started to do this with simple gambling games. Roulette, dice, and this is where you can immediately see, you know, the true distribution in the population, a uniform distribution, with dice and roulette as well. And by simply observing a huge number of these trials, you can see that the probabilities stabilize according to the distribution from which you are generating random numbers. So Monte Carlo simulation is synonymous to random number generation from a given distribution. And this is what we do in Monte Carlo simulation here as well. So every time you hear Monte Carlo simulation, please make sure that you know this is a very general method in statistics. You take a given distribution and you generate random numbers from it. This might be done in other applications as well in finance, but the most important application is option pricing. Why? And actually, the example you've given is also the same. In some cases, you have, for example, losses X according to a normal distribution, you have Y according to a T distribution, and so on, and you're interested in X plus, let's say, Y squared over X square root or something like this, and you have no clue what this new distribution looks like. And what you can do is you generate numbers from X, you generate numbers from Y, and then you just insert all those numbers into this function, and you can generate random numbers from this unknown distribution. This is also one famous application, or very important application. Every time you don't know what a new distribution looks like, if it's too complicated, you generate random numbers from its constituents, from its basic elements, and insert those simulated random numbers into this function, and you can generate random numbers from this new distribution for which you have no theoretical distribution. But let's come back to option pricing. What do we simulate here? What is the idea behind option pricing with Monte Carlo simulation? You take the stock price as 0. You have made an assumption on the underlying stochastic process. And what you do is, you start here and you simulate a path. You simulate another path. You simulate another path. You simulate another path. And you simulate. You simulate, you simulate, and simulate, and simulate, and so on. And you do this 100,000 times. And then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 potential future stock prices. And what you do then? You calculate how much worth would the option have been if this was the final terminal stock price. So you get C1, C2, C3, C11. And then, what you do then? You simply take the average. Then you get the average option price here. And what do you need to do then? Discount it. You need to discount it. That is what Monte Carlo simulation with an option pricing is all about. Take the average option payout under all these 1 million simulations, take the average, discount it, and you get an estimate for the option price. This is Monte Carlo simulation, really. When do we need it? Every time we have an exotic option. For plain vanilla option, this is overkill. Because we need a lot of computer power, we need good algorithms, and this is complete overkill if you can do it with Black-Scholes. So every time it's a plain vanilla option, we will not be doing Monte Carlo simulation, just for illustration here, but in practice you will never use it. So every time you have a more complicated option, an exotic option, and this is especially the case for path-dependent options, in which case the price or the payout of the option is depending on the path the stock price has taken, then you need Monte Carlo simulation. One example for such a path-dependent option is an arithmetic Asian option. This is given by the maximum of 0 or S bar, and S bar is the average stock price over the whole maturity of the option. So for plain vanilla option, we don't need it, but every time we have an exotic option, Monte Carlo simulation makes place. First of all, we need to simulate from the geometric Brownian motion. This is the basic starting point. We need to simulate this. So we start with the stochastic differential equation here. dst is equal to a dt plus b dwt. The simplest discretization is done by the so-called Euler scheme. What can we do? Delta dst is discretized by delta st. So this is st plus delta t minus st. And this is just parameter a times dt plus b times square root of delta t times epsilon. And we know the Wiener process has normally distributed increments. So the change in the Wiener process can be approximated by this change, a random number in the from the normal distribution times square root of delta t. Yeah, you remember this. The Wiener process was given by and x is a normally distributed random variable. Yeah? So we approximate this continuous change in time with a discrete change of time, and then this is the Euler scheme. However, obviously such an approximation comes with an approximation error. We saw before that we can use the geometric Brownian motion, and this actually yielded a totally different distribution. We had a log normal distribution, but not a normal distribution. So this is not the best way to do it. We can use Ito's lemma here, and if we take the geometric Brownian motion, the change in the logarithmic price, so the log return, is given by mu minus half sigma squared dt plus sigma dwt. If we substitute this, we get the expected logarithmic change from the initial price to the price st is given by nu t, and the variance is sigma squared times t. The expected relative change in price is the exponential function of mu t, and this variance is given by this. And if we can take these terms, we can actually integrate this exactly, and we get an exact solution. And this is the exact solution for the geometric Brownian motion. St, the price of the stock at time t, is given by S0, the starting price, times the exponential function of nu times t plus sigma times the integral from 0 to t of the Wiener process. And we can then discretize this, and we get this here. And this is what we'll use later on. The price of the stock at time t is the initial stock price times the exponential function of nu delta t plus sigma times delta, square root of delta t times a standard normally distributed random number. So what do? We know St, we have to generate a random number from the normal distribution. We insert it here, and we know delta t, sigma, and nu, those are known parameters, and then we can calculate the next step. Simply look at this very, very simple program. We want to simulate a path from a geometric Brownian motion. We need the starting price, we need mu, we need sigma, we need the maturity, for how long do we want to simulate, and how many steps, and how many paths. And REPL is just the number of simulations we want. And then this is the first point is S0, dt is t over n steps, nu dt, sigma dt, we can calculate this here, and then you can see st is st minus 1 times exponential function of nu dt plus sigma dt times rand n, and rand n is in MATLAB what is our norm in R. It gives you a random number from the normal distribution. That is why it's random number from a normal distribution, rand n. And let's do this now, 3 steps, 3 paths, these parameters, and this is what you get. And again, you can see, if I had shown you this and had not told you that these are simulated paths from a geometric Brownian motion, you might have guessed that actually this is a stock price, or these are 3 stock prices. So these are 3 paths, simulated paths from a geometric Brownian motion, and the rest is very simple. You simulate 10,000, 100,000 paths, insert it into the payoff profile, take the average, discount it, and you're done. And in the following, you can see we are doing it, for example, for a European style exchange option, and then we are here. You can see that we are doing this. This is Brownian. No, this is Black-Scholes, and here we are doing it with Monte Carlo simulation. And you can go through the programs at home. Just one slight comment here. In the end, I'm not calculating mean of the discounted payoff, but I'm doing norm fit. I'm fitting a normal distribution to the discounted payoffs. But as you know, the first and most important parameter of the normal distribution is the mean. So if I do norm fit and apply it to the discounted payoffs, what I'm getting is, I'm getting the price, which is the mean. But I can also calculate a confidence interval around this price, and I can see how good my approximation is. And here, if I do it here, you can see, for example, I get a Black-Scholes price of 0.8633, and here you can see by using 200,000 simulated stock prices, I get a price of 0.8552 and a confidence interval, and actually the Black-Scholes price is within the confidence interval. Yeah. And how can I improve it? Simply drive up the number of simulations. Let's not do 200,000, use 500,000. And in many cases, this will use up a lot of computer resources. This is why Monte Carlo simulation is so demanding. Okay, but we'll look at this next week. Do you have any questions concerning Monte Carlo simulation? Very simple idea. Just simulate until your computer is red hot burning. Insert it into the payoff profile of any derivative. Calculate the payouts of the derivative and take the average and discount it. The tricky part is that obviously especially in financial mathematics research, you want to use more sophisticated stochastic processes, not just geometric Brownian motion. And we are not doing it for a very simple plain vanilla option, but you're doing it for very complicated options and exotic options. And all this will drive up computation time. And if I just do, okay, let's do 1 million simulations, a computer will usually break down with complicated options. And then financial mathematicians will start working on improving these optimization programs and these simulations. And they will come up with more sophisticated processes from which you can simulate faster, more numbers, and how these programs can be improved on. Okay. If you have no questions, thank you for your attention, and let's continue here next week. Thanks.